Hello, everyone. I hope you're doing well, and sorry I'm not with you today, but I hope you guys are getting some good work done, ha ha ha, on your challenge problems. But this video is meant to be a follow-up to the initial 3 minutes or so that you watched on the Khan Academy website. So from that video, you would have learned that work equals force times distance. And I'm actually not going to write distance because we're dealing with vectors here, so I'm going to write displacement. So that would be like delta x or delta y. So W equals F times D. Now, when we're dealing with simple forces that are in the same direction as motion, it's very, very easy. And so I'm going to start with that, but then build into a force that's not applied in the same direction as motion. So this will be like the homework problems that you have. So suppose for the first example, along the ground, you're trying to push a box. And this is kind of a classic example because it takes work to push a box. So, my person has really long arms apparently. But if this person is pushing the box, and let's say that this box, it doesn't really matter actually what the mass is. We'll get to that when we talk about energy. But suppose my little stick figure man, woman, is pushing this box with a force of 50 newtons. And we're trying to push this box so that it moves a total of 30 meters, which is quite a long ways to push a box. 30 meters is approximately 90 feet, so you can imagine that that would take a lot of work. In order to figure out the work here, see how the force is in the same direction as the displacement? That's really important here. And so force is 50, so we're going to plug that in for F. And we're going to plug in 30 for displacement. And so we're just going to get 1,500 Newton meters. And hopefully you remember from the Khan Academy video that a Newton meter is defined as a joule, and which is just J. And you should have seen a joule in chemistry when you talked about energy. So our answer is 1,500 joules. Well, now I'm going to actually modify this just a little bit. So remember this situation, 50 Newton of force and a displacement of 30 meters to the right. So I should actually say this is 1,500 joules to the right and indicate some direction with that. Now let's have our stick figure man or woman. And assume my ground should be level. Is pushing, but for some reason it hurts his or her back to push this box directly across. And so what ends up happening is they're kind of pushing downwards at an angle. I'll make it a little bit different actually. Well, we'll keep that. Downward at an angle. And we'll say that this angle here is at an angle of 30 degrees below the horizontal. And so now that same force of 50 newtons is not being applied in this directly in the same line as the motion. Still want to move it for 30 meters. But work is actually defined to be only in the direction of motion. So if we're applying a force this way, it's kind of like we're wasting some of our force. We're pushing down into the ground. Well, the ground's going to push back. You guys know that from Newton's third law. And so part of our energy is being spent pushing against the ground. So hopefully intuitively, you guys know that by pushing like this, it actually takes a little more energy from you, but let's see what happens in terms of work being done. So what I want you guys to think about, we need to know this force that goes in the same line as our displacement. Hopefully this looks very, very familiar to you and you're like, oh my gosh, we're bringing back vectors, really? But yes, vectors are important. So hopefully you guys are experts, pros at this, and you see pretty obviously how we're going to get this. Hopefully you see that this is the x component of this vector. And so how did we find the x component? Well, let's make our triangle here. This is the adjacent side to the angle. And so this is going to be cosine. So we're going to do 50 cosine of the angle between them, which is 30 degrees. So there's actually another definition. If we go with this, we're going to end up getting that work equals the force in that direction of motion, the x, which is 50 cosine 30, times the distance, the displacement, sorry, which is 30. And cosine of 30, you should know that sine of 30 is 1/2, and this is root 3 over 2. But you can type this in your calculator. I actually don't have my calculator on me. I'll pause and get that number in a second. But there's an alternate form of this equation that you saw in the Khan Academy, force times displacement, which really will get us the same thing that we got here by vectors. So instead of just knowing that work equals force times displacement, we're actually going to say that work equals force times displacement times cosine of the angle, so theta. Theta is going to stand for the angle between force and displacement. So here, hopefully you can see that displacement is straight across and the force is applied at that angle, and so theta is 30. Theta is always going to be a small angle. So for instance, if you see something like 120 degrees, it's really going to be the complementary angle, the 60. So it should be something that's below 90. If I had just gone and done this formula, which hopefully you'll know this FD cosine theta one, we got the same answer, it's just rearranged a little bit. You get 50 times 30 times cosine of 30 degrees. Well, these look exactly the same. This is the commutative property. Make sure that when you guys are doing this, I know some of you in math go between radians and degrees. Since this is a degree, double check that you're in degree mode. So I'll do that calculation to get the answer real quick, and we'll be done. Okay, so this was roughly, and so in this example, since everything's really not based on sig figs, just to get you to understand what you're doing, this came out to be about 1299 Newton meters, which is the same thing as a joule. Obviously, this will be the same answer. Now, one thing that I want you guys to pay attention to, and we'll talk about this more tomorrow, notice how here we got 1500 joules. By doing it on the angle, we got a smaller number. Even though it requires you more effort, it actually is less work because we say that there is less work being applied to the box in that direction. That's really confusing to understand, but for now I want you guys just to know how to calculate this stuff. And so your homework is to do the practice A on page 162, numbers 1 through 4. All right, have a great day, and hope you enjoy snow. We'll see how much of it we actually get.